Okay, so today we're going to be discussing homework 6, which is about looking at unsupervised learning, transformations, and clustering, and dimensionality reduction using transformations. So first we're going to go over the code. We've got our imports. So I guess we'll just restart the kernel and then we'll run through it. Got our data set, normalize. Normalization is important for some and not for others, but to be consistent, you do it for all. And then for problem 1, we've got our our first plots for the PCA, and then the TSNE is working. It's slower computationally. And then we're going to go through problem 2, where we're doing our cluster tuning pretty much, the k-means, and we're producing our, let's see, we're running through getting our silhouette scores and fitting the k-means to the data, and then plotting. Okay, so plotting the elbow method here and the silhouette scores. And then down here we get to the silhouette plots, which I ran for all of them just to see what they look like. So as you can see, they get, well, it's still running, and it doesn't like for me to scroll through it when it's running. Okay, so that's still running. Anyway, it's all of them, and then you get to see, I guess I can do this. You get to see how the negative sort of, I guess, tails, I don't know, kind of grow larger and larger, showing more and more overlap in the silhouette plots. So as you get a greater level of detail, it just, all the clusters start beginning to really overlap. Okay, more and more. All right, and now we're going to get our average silhouette score, and then we're going to do the silhouette plot of our favorite one, which for me was k equals 4, and then we're going to get our core and boundary sample indexes, and then check those indexes, and then we're going to, okay, so I plotted, so here's the images, which, you know, the data set is based on CNN extracted features, and so the raw images aren't what k-means is using, so there's not a whole lot of, I couldn't really make any heads or tails of anything common with any consistency. I mean, like, there's 2 birds, and then there's a boat and a plane, which is tiny, in a blue sky, lots of background. Maybe this shape is interesting, but then over here it's not. Maybe that shape, but maybe that shape. I mean, but there's just not a lot of consistency for me to make any kind of heads or tails about the pattern. So I went ahead and plotted, looking at one of them closer, I went ahead and plotted the feature maps for the CNN to see what patterns could come out of that. And the way it's displayed here is a little less clear than the way I have it displayed in the report, and so we'll get to that. Okay, and then what's happening? Did I change a name somewhere? No? Maybe I didn't hit that. Maybe that was the problem. That was the problem. Okay, so then we're going into problem 3. Oops. Ugh, I hate the way. Now I don't know where I am. All right, let's start here. Oh, I went too far back? No. Okay. And then, okay, so now here's the heat maps compared to their images. And then I kind of just played with different ways of doing that. Oh, good Lord. I think because it's stuck. That's why it's getting mad at me. Okay, well, we go into problem 4, and which is the adjust rand index. And so we'll see those. And then here's the extra credit plots. Now let's take a sweet little time on something here. What is it? Oh, here. Okay, here we are. All right. Okay, well, we're going way over time, so, and we've got a lot to talk about. So, anyway, you see it working. So over here in the problem description, I'm going to go over on time because there's a lot to talk about in this particular. Oh, I went way far back. That was okay. In this particular homework assignment, there's a whole lot to talk about. So I hope you can accept that. So anyway, we are looking at the principal component analysis, the TISNE embedding, probability-based embedding, and the k-means clustering. We're using the CIFAR 10 revisited dataset, which is a reconfiguration of the original raw 10,000 images into 128 dimensional feature vectors. And then we use standard scaler to scale the data. I provided here a tree of all of the, I rewrote some of it poorly, but to match our structure for the course, but these are all of the algorithms that have been studied in the course, and how the algorithms that we're currently under review are placed within that larger family. And then the larger family that we haven't discussed, but just to visualize it. Okay, and then here we go over unsupervised learning, which, is just not having labels, basically, and not being able to, during training, compare predictions to labels and then iteratively self-correct with those labels. So here you're doing other techniques to sort of to reconfigure the data into clusters that aren't necessarily related to classes or the true labels, but they can correspond to it, and which is basically what we're sort of overviewing in this study. So PCA is a linear algorithm, and it transforms the data into first eigenvectors and eigenvalues, and then orders them by their eigenvalues, which is a iterative process in and of itself and uses gradient descent. But then you take those eigenvectors and you order them, and then you select an n-number amount of those, or more specifically, I think it's init. Or no, sorry, that's the wrong, no. Okay, so you select the number of eigenvectors that you want, and those are called the principal components, and those describe various non-redundant lines within the data that describe the maximum amount of variance within the data. And then those are then matrix multiplication magic happens, and we come up with a new each sample is multiplied with this, so that with the principal component matrix to provide a transformation into whatever dimensional space we've decided on. So and then the visualizations that we go over are 2D, so we do 2D. You do it into 2D or 3D so that you can visualize it. Okay, that's enough of that. All right, so now we go into manifold learning and TISNE, and the difference with TISNE is that instead of doing a functional transformation that projects the data, instead it's using probabilities to calculate how likely one data point is to choose another data point in low dimensional space. So in low dimensional space, it uses a new student t distribution, so that which is different than Gaussian and allows for distant points to still get some probability. And the closer the points are, it uses Color-Liebler cost function to penalize distances that were close in the high D that end up not close in the low D, and then iteratively updates those until the difference between the high D and the low D is minimized. Okay, so and then these are how it works. I've really broken it down. I really wanted to understand these, so I really broke them down into every mathematical step. And then, you've got your plain English description, why it matters to the overall algorithm and outcomes, the math that's involved, the variables explained, and the ultimate result. And I've done that for the TSNE, the PSA, and the k-means. So, and then the k-means is now our clustering, which is the other form of unsupervised learning. The other two were transformations. This is clustering. So clustering basically randomly selects however many user-defined centroids, or k, your variable k, or actually it's in clusters in scikit-learn, but it's k everywhere else. So then you take the number of k, and it randomly selects the from the just random data points, and then there's a smart random that scikit-learn provides. But I ran that the smart random, and it didn't make any difference for this particular study. So, but it picks them at random and then recalculates then it finds all the data points that are closest to those random k samples that were selected. After that process is completed, it recalculates the mean centroid of all the data points that are currently connected to that particular previous centroid, and then that new calculation, that imaginary mean vector, is now the new centroid. Then it does this all over again and recombines them. And it keeps doing this until moving around the centroids and recalculating them really has a minimal effect or no effect at all. And that is determined through the sum of squared error. Okay, so coming down here, we go over the evaluation metrics, and here are the projections of the PCA in 2D and the TSNE in 2D. Of course, you see more overlap in the PCA because it's a linear projection, and it doesn't have the capacity for distinguishing between those non-linear, like determining non-linear separation between classes. So then in TSNE, you've got the ability to iteratively and using gradient descent sort of create those curves in the data and get more of that nonlinear separability. And that's why you see these like bigger areas of and less overlap between the two. And then of course it retains those small neighborhoods, and so you get all these little clusters. All right, and then here's the similarities and differences. I kind of, you can see here basically what's happening here. This is very similar. This is very different. All right, and then every shade between. All right, so in the analysis, I kind of gave a summary there. Silhouette, we've got our silhouette plot. We've got our plotted silhouette scores along the SSE. So as the SSE decreases, so too does our average silhouette score. So we want our average silhouette score to be high and our SSE score to be low. So the compromise that I chose was k = 4, because there's a big drop off in the silhouette score here, and that's kind of where it begins to get less and less. But the silhouette score I tended to think was more important because of the way it it basically describes the cohesion of the clusters and the separability of the clusters, and the way that it is calculated and what it means for the clusters themselves. Okay, so then when we redid this for the 20D, and everything got better. You know, the average silhouette score, the maximum silhouette score, the SSE scores, they all improved. When the 128 CNN features were reconfigured and compressed by into the centroids and whatnot, put for the PCA into 20-dimensional. So then now we're taking a look at individual images. Again, I didn't find these to be very useful, the raw images. Here's the 128D. I found that there were these diagonal kind of portions. So it's almost like there's two diagonal lines here and here, here and here, and vaguely here and here and here. And then over here we've got kind of 4 diagonal lines across these. So 1, 2, 3, and 4, 1, 2, 3, and 4, and so on and so forth. Here you've got lower contrast, and you kind of have this little blob up here. And then each one, I didn't talk about this in the report, but each one kind of has this pale dot that's in a similar spot. Over here you've got sort of this, like, almost like maybe it's more like, I said it was an ellipse, but maybe it's more like a diamond actually. That's kind of forming along here. So those were the patterns that I may have been able to visually determine here, but again, they're so loose that it's hard to say that those are the patterns. But once you get over to the 20D and compare it to that and that experiment, now all of a sudden, even though you find there's maybe a little bit more relatability between the images in the 20D, but it still kind of remains fairly scrambled. However, when you look at the heat map, now you see in the principal component, these represent the principal components. Now you can see very clear patterns emerging. So you've got every single one of these has a black dot. Every single one has like an orangey pale dot. Every single one has a pale dot, and then a darker dot here, and the rest of it's sort of like this, like mid shades of purple to orange. And then that's just an example, and you can make your own inferences for the rest of them. Down here, this is the analysis, and I kind of talked about the similarities and the distribution of the classes within each cluster. And then down here we've got our boundary samples, and I basically talk about how you can kind of see some of the things that I talked about in the core samples, but in a vaguer way here, with the exception of cluster 1 really doesn't have very much discernible patterns, except for maybe that rogue dot. Maybe that's it. Maybe it's the rogue dot. I guess that's it. Yeah. Okay, so anyway, coming down here, the ARI is the measurement of, this is where you're actually like going to make predictions with the clusters. And wait, do you make predictions? Hold on. I just got myself turned around here. So you're comparing it to the two true classes. Okay, no, it's not necessarily making predictions, but it's just taking the clusters and seeing how they match to the true class labels. So you're passing in the true class labels, and it's saying like, okay, does this cluster, how many clusters correspond in this way? And so now you see that the ARI picked k equals 5 as its favorite, which has a very significant increase in the ARI score, a fairly significant, well, when you look at the actual numbers, it's not actually that significant in the average silhouette score in the 128D, but but it is a drop compared to everything else. And so you get 0.693. I'm not sure what a I don't really know what a great ARI score is, but given the fact that it accounts for chance and subtracts that out, I feel like 0.693 is probably pretty good. So, but the SIL score is ridiculously low, 0.037. So when we come over here, the SIL score has increased threefold. It's still very low, but it is a threefold increase from this one, and the ARI score didn't really drop that much. So this became the favorite configuration, and now down here we take that configuration, we reproject it into 2D space, and we talk about the classes and the concordance with the class and the clusters, and basically the general conclusion is that PCA is really great for dimensionality reduction and passing on to supervised models, and then t-SNE is really great for actually looking at the cluster concordance that resulted from running the k-means clustering algorithm or whatever clustering algorithm, and then projecting that into, well, it's not a projection for t-SNE technically, but I think people refer to it like that. So it's just the way it's the 2D representation that t-SNE offers gives a lot more insight into what happened during the k-means clustering and how well it I guess performed might be kind of the wrong word to use, but how well its clusters are mapped to the original ground truth labels. Okay, that's it. Thank you.